Hello students, after studying vector and calculus, it is now time to start the real physics. The first part of physics that we will take up is a very important part called mechanics. What is mechanics? Mechanics is the study of motion. We study mechanics in two parts, kinematics and dynamics. When we study kinematics, we study motion without referring to its cause. That means when we are studying kinematics, we will be basically describing motion in terms of position, velocity, acceleration, the distance covered, speed, etc. We will not be assigning it any cause in terms of like force or mass or energy, etc. Okay. When we study dynamics, we talk about the laws of motion, inertia, and all the Newton's laws, and then the applications based on that, conservation of momentum, conservation of angular momentum, and all that things. Alright, so first we will start with kinematics. The name of the chapter, the first chapter of mechanics is kinematics. Alright, so let's focus on kinematics. What are the basics of kinematics? Some of the things you already know. This is the position vector. Suppose we have a particle at point P. Point P has coordinates, let us say x1, y1. This is our origin. So this vector from O to P is called the position vector. Now suppose the particle moves like this and it goes from here to here. After some time, the particle is found to be at point Q. Position vector of Q is this. Point Q has coordinates x2, y2. So the distance traveled, displacement is given by this vector. This we have already studied in the vector. So position vector and the displacement vector. If I call position vector r1 vector, I can write it in terms of coordinates as x1 I cap plus y1 j cap. Final position vector r2 vector from O to Q. This r2 vector can be written as x2 I cap plus y2 j cap. So the displacement vector delta r vector will be given by r2 vector minus r1 vector as x2 minus x1 I cap plus y2 minus y1 j cap. So these are the things which we have already studied. Now distance, what is the distance travelled by the particle? Is the distance travelled by particle simply magnitude of this displacement vector delta r? No, it is more than that. Distance travelled is actually the length of this path along which the particle has moved. And you can see that in this diagram, this L is clearly greater than the magnitude of displacement vector. So we can define the next term as the distance. Distance travelled. This distance travelled is the actual length of the path along which the particle has moved. And clearly this distance travelled L is greater than or equal to the magnitude of delta r vector. Magnitude of the straight delta r vector. In this diagram you can see that L is greater than delta r vector, but in a special case it can be equal also. Which special case? when the particle goes along a straight line path directly from P to Q. In that case, L will be equal to the mod of delta r vector. In general, we can say L is greater than or equal to the magnitude of delta r vector. So distance traveled is greater than or equal to the magnitude of displacement vector. Speed, rate of covering distance is known as speed. अब देखो फिजिक्स में रेट बहुत सारी आएंगी. ये पहली रेट आई है, रेट ऑफ कवरिंग डिस्टेंस को हम स्पीड कह रहे हैं. रेट ऑफ चेंज इन पोजीशन आ जाएगा वेलोसिटी. रेट ऑफ चेंज इन वेलोसिटी बाद में हम पढ़ेंगे एक्सेलरेशन. बाद में एक चैप्टर में आएगा रेट ऑफ फ्लो ऑफ चार्ज विच इज करंट. फिर एक आएगा रेट ऑफ डूइंग वर्क, पावर. तो इस तरीके से कई सारी रेट्स फिजिक्स में आएंगी. रेट के बारे में अगर हम कुछ चीज़ें पहले से ही सीख लें तो सब जगह हमें फ़ायदा होगा. तो रेट जहाँ भी आएगी ये दो टाइप की होगी, इंस्टेंटेनियस और एवरेज. जब हम बात करते हैं इंस्टेंटेनियस रेट की, इस केस में हम बात कर रहे हैं इंस्टेंटेनियस रेट ऑफ कवरिंग डिस्टेंस, तो वो डिफाइन की जाएगी एक इंस्टेंट ऑफ टाइम के लिए. फॉर एग्जाम्पल, अगर कोई व्हीकल मान लो इस पॉइंट P से स्टार्ट करके इस रास्ते से Q तक जाता है, पॉइंट A पे उसकी स्पीड अगर हमें बतानी है, P से लेके A तक उसका अगर लेंथ ऑफ द पाथ लेंथ L आ रही है, तो dL/dt जिस रेट से ये पाथ लेंथ बढ़ रही है इस मोमेंट पे, वो है उसकी इंस्टेंटेनियस स्पीड dL/dt. अगर हम बात कर रहे हैं एवरेज स्पीड की, तो एवरेज रेट जब भी हम निकालेंगे उसके लिए हमें एक टाइम ड्यूरेशन दिया जाएगा. तो मान लो कि पॉइंट A पे ये किसी मोमेंट पे है, कुछ देर बाद ये पॉइंट B पे यहाँ पर आ जाती है और हमें इस ड्यूरेशन के लिए एवरेज स्पीड चाहिए. तो फिर हम A से B तक ये जो पाथ लेंथ बन रही है कर्व्ड इस तरीके की, ये वाली पाथ लेंथ है मान लो डेल्टा L. तो हम कहेंगे कि एवरेज स्पीड for this duration is delta L divided by the time taken to reach from A to B, which is delta T. So this is the meaning of average speed, instantaneous speed and average speed. Now, if we take a practical example, if we are traveling by say a car, तो उसमें एक होता है स्पीडोमीटर. वो जो पॉइंटर होता है, तुमने देखा होगा, जैसे जैसे गाड़ी की स्पीड बढ़ रही है वो पॉइंटर 0 से 20 किलोमीटर पर आवर, फिर 40 किलोमीटर पर आवर, 60 किलोमीटर पर आवर की तरफ जाता है. तो वो जो पॉइंटर की रीडिंग है किसी मोमेंट पे, वो उस व्हीकल की क्या है, वो है इंस्टेंटेनियस स्पीड, क्योंकि वो एक पर्टिकुलर मोमेंट के लिए बताई जा रही है. जैसे जैसे पॉइंटर मूव करेगा वो स्पीड बदल रही है. अच्छा, एवरेज स्पीड किसी व्हीकल की अगर हमें निकालनी हो तो कैसे निकालेंगे? उसके लिए काम में आएगा उसका जो माइलोमीटर होता है, जिसमें वो किलोमीटर्स की रीडिंग आती है. व्हीकल जैसे मान लो एक जगह से स्टार्ट हो रहा है पॉइंट A पे, हमने उसकी रीडिंग नोट कर ली कि भाई अभी ये गाड़ी इतने किलोमीटर तक चली है. फिर वो A से B पे आ गया तो उसकी रीडिंग कितनी बढ़ गई, कितने एक्स्ट्रा किलोमीटर उसने A से B के बीच में ट्रैवल किए हैं, वो हमें मिल जाएगा डेल्टा L. अगर हम उसको डिवाइड करें इस टाइम ड्यूरेशन से, यहाँ से यहाँ तक, यहाँ A से B तक पहुँचने की जो टाइम ड्यूरेशन है, जिसको कि हम अपनी घड़ी से भी देख सकते हैं कि भाई A पे हम मान लो 10:15 पे थे और B पे अगर हम 11 बजे पहुँचे हैं तो 45 मिनट लगे, 3/4 आवर. तो इस तरीके से हम डेल्टा T निकाल के और एवरेज स्पीड को कैलकुलेट कर सकते हैं. तो इसकी डेफिनेशन जो है स्पीड की हमें ध्यान होनी चाहिए. इट इज़ द रेट ऑफ कवरिंग डिस्टेंस. Velocity is defined as the rate of change in position of the particle. Now, at any instant, suppose the particle is at point A and then it is moving along this path. Now, at some point it is at some instant of time it is at point B, and suppose if we have to find the average velocity for the duration in which the particle travels from A to B. So average velocity will be total change in position vector, which is also called the displacement vector, delta R divided by delta T. And if you want to find instantaneous velocity at any instant of time, it will be, you can take the limit delta t tends to 0, and it will, what it becomes is, it becomes the derivative of position vector r. Now, if we look at the average velocity from A to B, this is the displacement vector delta r, and you can notice that the displacement vector delta r has a magnitude less than the distance travelled delta L here. So, the magnitude of this average velocity vector is not same as the speed of the vehicle or the average speed of the vehicle for this duration. This is in fact less. If you find the magnitude of average velocity, V average magnitude, if we are talking about, this is less than, or it may be equal in a particular case to the to your speed, It will be equal only if the particle is going straight from point A to B along a straight line path directly from A to B. Only in that case delta L and delta R, they are equal. Only in that case speed and magnitude of average velocity will be same for a duration. But if in general case, say for example this one, delta L is greater than delta R, so accordingly in the shown diagram the magnitude of V average will be more than the average speed. Now how do we compare the magnitude of instantaneous velocity to the speed? See, for finding instantaneous velocity, I have to reduce this time interval to a very, very small value, which we call limit delta t tends to 0. That means if I take the interval to be, say, from here to here, you can see that if I take this small interval, the difference between path length and the straight distance has become very small. Now, if I take this point very, very close to A here, this difference between delta R and delta L will vanish if in this case, in the case of limit delta t tends to 0. That means if the points are very, very close, you can see there will be hardly any gap between delta L and delta R. It's not visible in this diagram, but if the gap is large, as we have taken point A and B here, clearly delta L is more than delta R, magnitude of delta R, but in the limiting case, this difference simply vanishes. It means that magnitude of instantaneous velocity, which is the magnitude of dr by dt, is same as the instantaneous speed. By the way, here the speed was your average speed. This was your average speed. We were comparing magnitude of average velocity to average speed. This is instantaneous speed. So the magnitude of instantaneous velocity is equal to the speed at that instant. If the vehicle's speedometer is showing 60 kilometers per hour and the vehicle is moving towards north, if I just put the direction, if I just attach the direction to the speed, I get velocity. So as far as instantaneous values are concerned, velocity and speed, they have same magnitude. But in the average, velocity vector will have a magnitude less than or equal to the average speed. Direction, of course, you can see direction of average velocity will be same as the direction of delta R vector, or you can say the displacement vector from A to B. So average velocity vector has the same direction as the displacement vector, whereas the direction of instantaneous velocity, you can see as the 2 points are approaching each other, if I take this point very, very close to it, the interval becomes very small, this becomes a tangent. So the direction of instantaneous velocity is along the tangent to that point in the or that point of the trajectory. If I want to find the instantaneous velocity at point B, its direction will be again tangential to this point. Say at point Q, it may be something like this. It will be tangential to the trajectory at that point. Next we come to acceleration. Acceleration is defined as the rate of change in velocity. Now again we can have instantaneous acceleration or we can have average acceleration. Average acceleration is defined as the total change in velocity, which means the final velocity minus initial velocity of particle divided by the time duration. So these are the definitions. These are the definitions of average acceleration and instantaneous accelerations. See, definitions are extremely important in physics because they are never wrong. See, if you have a formula, that formula may be valid in certain condition, it may not be valid in certain condition. For example, you must have heard of that equation V is equal to U plus AT. That gives you acceleration as V minus U upon T. Now, that equation will work only if acceleration is constant. That will work only if the acceleration is constant. But this basic definition of instantaneous acceleration, this will always give you the correct result. This is the instantaneous acceleration, and this one is the average acceleration. Average acceleration is, for average acceleration, you just need final and initial velocities. So for example, in this situation, if the final velocity of particle is V2, initial is V1, knowing these two, we can calculate acceleration. We don't need velocity at each and every point. But the acceleration at every point can have different value. You can have a situation where the particle is moving with constant speed and its direction is changing. Even in that case, acceleration will be non-zero. So whether the magnitude changes or direction changes or both change, a vector changes, and if velocity is either changing in magnitude and direction, you will have some non-zero instantaneous acceleration for it. Let's take up an example now. Let's take an example which will illustrate all the quantities that we have defined. We have a situation where a person is running along this circular track, maybe in a park. Radius of the circular track is 120 meter, and he completes one circle in 4 minutes. It is given that the person is moving at a constant speed such that he completes one circle in 4 minutes. Now, for the top half of the circle, that means from A to B, we just have to consider this half circular part. For this part, we have to find these 5 things: displacement, distance traveled, average velocity, average speed, and average acceleration. So the person is running along this, and he is moving at a constant speed. He is moving at a constant speed. Of course, velocity is not constant because the direction is continuously changing. So we are taking this as our moment t equal to 0. And we are interested in this part of his journey from here up to here. Okay, you can pause it and attempt all these parts, and then we will see what are the solutions. Okay, so the initial parts you must have found easy. First is displacement. See, displacement, remember, is a vector quantity. So your answer to this part 1 must be vector. Okay, if you have given an answer only in terms of magnitude or a scalar quantity, your answer is definitely incomplete. If it is not wrong, it is surely incomplete. So you have to tell magnitude as well as direction. See, displacement is this straight line vector here, okay, from point A to point B. Length of this vector is clearly double of the radius, so 240 meters, and the vector is pointing in this direction, which is the west. East is this way, north is this way, this is the west. So answer to the part 1 is the displacement vector delta r vector is, you can say, 240 meters towards west. 240 meters west. Second part, distance traveled. So distance traveled is the length of this path, which is what? Which is half of the circumference. So the distance traveled L, we can say, will be half of 2 pi r, that means only pi r. So this will be 120 pi meters. And of course it is a scalar, so no question of direction here. Third one, average velocity. Average velocity, we know, is defined as delta r vector, displacement vector upon the time duration. Displacement we have already got as 240 meter west. We just have to divide this by time. Question says the person completes the circle in 4 minutes. So delta t for covering this half circle will be 2 minutes. 2 minutes, which we can say is how much? 120 seconds. So the value of average velocity becomes 240 meter. See, I can refer to this in terms of our unit vectors also. If I am taking origin here, east is x-axis and north is y-axis. So I can also write this as minus j cap. So I can denote the delta r vector as 240 meter times minus j cap divided by, or rather minus I cap I should take. This is west is minus I cap. So 240 meters minus I cap divided by the time duration, which is 120 seconds. So the average velocity of the person becomes 2 meter per second minus I cap. Minus I cap means towards west. Part 4 of the question, average speed. Average speed is simply the distance traveled by the particle upon the time duration. So average speed, we can write this as 120 pi meter, which was the length of the path. Time duration is 120 seconds. So this is simply pi meters per second, 3.14 approximately meters per second. So that is his average speed. Now to the fifth part of the question, average acceleration. A average, we know, is final velocity minus initial velocity, that is change in velocity divided by the time duration. Now particle is moving at a constant speed. So remember, velocity is a vector, so we will need magnitude as well as direction. Direction is tangential, so final velocity when the particle is at point B is towards south. When the particle is at point A, it is towards north. We have to draw tangents at these points. About the magnitude of instantaneous velocity is simply the speed. So secondly, we also know that the person is moving at a constant speed. So if the speed is constant, that means its average and instantaneous value is same. So the average speed which we have calculated, pi meter per second, is also the instantaneous speed, or you can say this is also equal to the magnitude of velocity vector of the particle. And magnitude of the velocity is of course constant. So v2 vector and v1 vector, they both have same magnitude, which is pi meter per second. And direction, we can see from the diagram, final velocity or the v2 vector has a direction of minus j cap, v1 vector is plus j cap. So we can write this as pi meter per second, that is the magnitude, and the direction is minus j cap, minus v1 vector has the same magnitude, pi meter per second, direction is j cap, and we have to divide this by the time duration, which is 120 seconds. So it comes out to be minus 2 pi j cap by 120 will become minus pi j cap by 60, and the unit will become meter per second square. So this is the value of average acceleration from A to B. The direction of average acceleration is towards south. Minus j cap means towards south. I have added some more parts to this question. We have to find velocity of the particle at these particular instants at t equal to 30 seconds, t equal to 60 seconds and t equal to 90 seconds. So these are instantaneous velocities. When you are given a duration of time, you can find an average velocity for that duration. When you are given an instant of time, you can find instantaneous velocity for that duration. So now we already know that the particle is moving at a constant speed, which means the magnitude of velocity will remain same, which is equal to speed, and we already know that speed is how much it is, pi meter per second. So magnitude of velocity vector at all these instants is same, and that is pi meters per second. So we just have to find the direction, or you can say find the unit vector and attach the unit vector to this magnitude, and we will get velocity vector. So now in order to get the direction, we should first find the position of the particle at these moments. Now finding position is quite simple because the total time duration from here to here was 120 seconds. So at 30 seconds it must be 1/4 of this, so it is somewhere here. This angle should be 45 degree. In 120 seconds it covered your 180 degrees, so 1/4 of that is 45 degree. At t equal to 30 seconds, particle is here, the velocity must be directed something like this. At t equal to 60, half of 120, it is halfway, that means somewhere here, t equal to 60 seconds, the velocity has a direction. Now this is easy one, you can see it is towards west, and at t equal to 90, the remaining angle, that means 30 seconds before reaching B, this remaining angle should be 45 degree. So the direction of velocity will be somewhat like this. So these are the 3 points. Now out of which the second one is quite easy. At t equal to 20 seconds, velocity at t equal to 60 seconds, we can say is pi meter per second, and the direction is minus I cap, towards west. Let's take the instant t equal to 30 now. What we need is just unit vector in this direction. Now this direction is making an angle of 45 degree with the y-axis. Alright, and you can clearly see that the y component is towards north and the x component is towards west. It is between north and west. So unit vector in this direction will be, you can say, cos 45, because 45 is the angle it is making with the y-axis. So cos 45 j cap, and sine 45 degree minus I cap. So this is the unit vector. I just have to attach this unit vector to this magnitude and I will get velocity at t equal to 30 seconds. So it becomes pi meter per second multiplied by minus sine 45, so it is minus 1 by root 2, minus 1 upon root 2 I cap, and plus 1 upon root 2 j cap. So this is the velocity at t equal to 30 seconds, about t equal to 90 seconds. That means this point, you can see both the components, x as well as y component, both the components are negative. It is pointing towards southwest. It is pointing southwest. So both the components are going to be negative. This angle is again 45 degree. So you can see that velocity at t equal to 90 seconds will be pi meter per second, which is the magnitude, times minus cos 45 I cap and minus sine 45 j cap. So finally you can write this as pi by root 2 meter per second minus I cap minus j cap. So these are the magnitudes, these are the velocity vectors at t equal to 30, 60 and 90 seconds.